Greetings, welcome to IT Basics. Today we're going to have a look at the very basics of binary and converting decimal into hexadecimal into binary. We like our Deca sort of number system because we have 10 digits and we're kind of used to it. We're used to counting in units of 10. It comes natural to us. So that's what we have. When we're talking about a computer, we aren't talking about a complex human brain, we're talking about a very simple on and off switch. Computers, the history of computers stems from cards, from punch cards. So basically the choice was either card or you punch a hole in it and you've got a hole. So you've got two options. You've either got a piece of card or you've got a hole in there. So that's your only two options. And depending on how many holes are in the card and where they were placed would depend on the value that it would equate to, the card would equate to. But essentially, it's either no hole or a hole. They're your two options. It's either yes or no. It's either true or false. It's Boolean. It's either true or false. It's either 1 or 0. In computers, as you know, computer language is 1 or 0. We can either use a 1 or a 0, an off or an on. That's the only two options we've got, which doesn't leave a lot of options. I mean, you could look at Morse code. If you're looking at Morse code, that's a Boolean. It's either sound or no sound. So how did we manage to take that on-off, that Boolean, the yes or no, the two choices, and turn them into the world of technology that we have today? So we did that through this binary system. So let's take a light, okay? So this is a light. Okay, so it's as simple as it gets. It's either on or it's off. If it's on, we'll call that 1. If it's off, we'll call that 0. So we're not going to get very far with that because we have two options, 1 or 0. That's all we can do with it. We could do Morse code with it, but that's probably about it. So what we need is more lights. We actually need more lights. So why don't we add some more lights? 4, 5, 6, 7. I might put one on this side just to make it nice and even. So there we go, that's better. Now we've got 8 lights. This is an 8-bit digit. This is what's referred to as an 8-bit digit. At the moment it's 0 because when the lights are off, it's 0. And when you've got a whole bunch of zeros, you still got 0. So 0 plus 0 plus 0 plus 0 plus 0 plus 0 equals 0. Now, how do we turn this into bigger numbers? So this one here, we're going to call it 1 because that's what it originally is. So if it's on, it's 1. If it's off, it's 0. Sounds pretty straightforward. That makes sense. That's what it was to begin with. We could assign this one, we're going to have to assign this a different value. We could assign it, for example, 2. So when that's on, it's 2, and when it's off, it's 0. And then we can do 3, and then we can do 4, and then we can do 5. But if we're going to start using big numbers like 100,000, a million, or all the numbers that are involved in computing, we're going to need a hell of a lot of lights. Like, it just does not make any sense. So how can we condense it into this sort of 8-bit digit? One way to do it would be to double it as we go, and that's exactly what they do. So they take 1 and they double it. So if you double 1, you've got 2. So this light will be 2. If it's off, it's 0. If it's on, it's 2. Let's double that again. So this one will have the value of 4. So if that light's on, it'll be 4. If it's off, it will be 0. We double that again. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. This is getting tricky because unless you know your 2 times table, it's going to start to get tricky. So 64 and 128. So that'll do. We can't really go further than that. That's fine for now. You can get 16 bits and on and on and on. But at the moment, we'll work with our 8-bit unit here. So if that light switched on, it's 1. If that light switched on, it's 2. 4, 8, 16, 32, 64, 128. Now we have larger numbers to work with. So this is good. This is good. So how do we write it? How do we turn this binary into these numbers up here. We turn the lights on. As we said before, we've got two choices, on or off. So if we want the number 1, let's turn that light on. Bang. So we turn that on. That is how you write 1 in binary. You simply turn the last light on. So it's 0, 0, 0, 0, 0, 0, 0, 1. In an 8-bit digit, that's how you write the digit 1. Just a 1 at the end, the last one. How do we get 2? So the formula, which is not very technical, but it is the formula. If you're trying to find a number, you have to find either the same number, obviously, or a number that's under it. If you turn the light of a number that's over it, say for example we're after 30 and we turn on the 32, well we've gone over, that's not going to work, we've gone too far. So you have to turn on a light that's either the same as the number you're looking for or less than it. And you go in that order, so I'll show you what I mean. So let's find the number 2. So you got everything's off again. How do we get 2? Let's see if we've got 2 there. Obviously we do. So it's a matter of just simply turning that light on. So that light goes on and now we've got 2. This is how you write 2 in binary. 8-bit binary is 0, 0, 0, 0, 0, 0, 1, 0. That's how you turn it on. How do you do 3? You turn on the 2 because you can't turn on the 4 because that's over. So you have to turn on the 2. So we're looking for 3. We've turned on the 2, so we can take 2 away, which still leaves 1. So we turn this one on as well. So now we've got 2 lights on. We've got the 1 light on and we've got the 2 light on. When we add those 2 lights together, it equals 3. So this is 3, written in binary. That's 3. How do we get to 4? That's pretty easy. We can see there's a 4. We turn that on, and that's 4. So basically, that is how we write 4 in binary. 0, 0, 0, 0, 0, 1, 0, 0. That's 4. How do we do 5? So we can't turn the 8 on, so we'll have to go with the 4 again, so that stays on. Now you've got to go to the next one across. Let's have a look. What do we want? We want 5 minus 4. We'll take away that 4 now. We're left with 1. That doesn't work. That's too big. We can't turn that one on. That one's the next one we can turn on, 1. If we turn on 2, we'll end up going to 6. So we got to turn this light on, the 1 light on. That's how you write 4 in binary. We've got the 4 light switched on and we've got the 1 light switched on. 4 plus 1 equals 5. Let's keep going. What about if we want 6? So we'll turn them all off again. We've got back to 0. What do we do if we want 6? Well, we can't turn the 8 on because that's too big. We can turn the 4 on. We're looking for 6. Let's write that down. We're looking for 6. We can turn the 4 on. Yep, that's on. So 6 minus 4, we've got 4 already, leaves 2. There's a 2 there. So let's turn the 2 on. That equals 6. So that's how you write 6. 4 plus 2 equals 6. That's how you write 6 in binary. 0, 0, 0, 0, 0, 1, 1, 0. That's how you write 6. What about 7? We're looking for 7. I mean, don't bother turning the 8 on because it's still higher than 7. So we've got 4 would be on, 2 would be on. All we have to do is turn on the 1, obviously. We just had to add 1 to 6. So that's how you have 7. If you add 4, 2 and 1, you've got 7. So that's how you write 7 in binary. It's 0, 0, 0, 0, 0, 1, 1, 1. That's how you do it. Now, what about if we've got a really big number? Why don't we go crazy a little bit and go with a really big number? So why don't we go for like 100, because that's a big number. Like, you know, when I was at primary school, 100 was like one of the biggest numbers. And like if you had $100, you were pretty much rich. So that's a big number. So how do we do 100? Okay, so we can't turn this last light on. That's 128. That's too big. No, we can't turn that on. We can turn this one on. 64 is less than 100. So we turn that one on. So now we've got the 64 light on. We have to subtract that from 100. So what do we got there? We've got 36. So we've got 36 remainder. So we still have to find 36. So after 64, we've got 32. That works. Okay, 32. Yep, let's turn that light on. 32. So now we've got to take 32 from 6, which leaves 4. We've got 4 left. So let's have a look. Can we turn the 16 on? No, that's higher than 4. Can we turn the 8 on? No, that's higher than 4. Aha, we've got 4 here, right here. Beautiful. Let's turn that light on. So this is how you write 100. You've got the 64 plus the 32 plus the 4. So it's 0, 1, 1, 0, 0, 1, 0, 0. That is how you write 100 in an 8-bit binary number. So that is how binary numbers are written. That's how we're either able to get lots of bigger numbers, and if you extend the lights and keep doubling that number, you can extend it and extend it. And that's how we're able to turn a simple on-off into many countless combinations, which has led to the amazing technology that we have today. I hope that makes sense. I hope that helped. Thank